This part, it will be a little bit long, guys, because we will go deeply in the explanations. We have a lot of stuff to explain. So don't be demotivated, guys, and don't give up to learn. One way to answer these two MQs in constant time, say by pre-computing all the answers of all the blocks. So each block will compute all the answers of each range, range minimum query. We have done this in the beginning of this lecture, guys, by using the same approach, but on the whole array. We built a 2D array of size n plus 1, I think, at that moment. But this will store all the answers of each block. Here we go and store the positions. The position of the minimum of each block. For example, here, if I take this block, we're going to pre-compute all the answers here. The rows will be the left boundary, the columns will be the right boundary. If, for example, I want to answer the minimum from 1 to 3, I think here is 4, this is 4. From 1 to 4, I have to see here 1, this row, and 1, 2, 0, 1, 2, 3, 4. Okay, the answer is here. I can get it in constant time. Let's see what's the time complexity of this preprocessing. The number of blocks is n over log base 2 of n. And each block, the size of each block is log of base 2 of n times log base 2 of n. What's the size? The size of this array is the size of the block here. This times this. So the whole time complexity, we can compute it very quickly, is n log base 2 of n. But here, keep in mind, guys, we want a preprocessing in linear time. This is the whole goal of this algorithm. So we have to improve the querying here, the time of the preprocessing of the arrays of the blocks here in linear time. How to do that? We have to normalize the blocks. These blocks, we have to normalize them. What's normalization first? The goal of the normalization is to attribute types to the arrays in a manner that the arrays of the same type will have the same preprocessing and the same MQs. So we're going to divide blocks into types. The arrays or the blocks of the same type will have the same preprocessing and, of course, the same MQs. How come this? Why we can use this? Because it's obvious if you have two arrays of the same normalization, then all MQ answers will be at the same position for X and Y. So we can do the same preprocessing. on the both arrays. Let's take these two arrays. What does mean the array have the same type? Let's analyze this. As you see here, the first array, I have here 5, then 2, lower than 5, then minus 3, lower than 2 and 5, and 4, lower than 4, sorry, greater than minus 3, greater than 2, but lower than 5, and 0, lower than 4, greater than minus 3, lower than 2, lower than 5. Let's see the array on the right here. We have 36. I have 21 lower than 36, 2 lower than 5. Then 8 lower than 21 and 36. So minus 3 lower than 2 and 5. 25 greater than 8, greater than 21, lower than 36, so greater, greater, lower. So here, greater, greater, lower. 10, lower, greater, lower, lower. Lower, greater, lower, lower. As you see, we can say that these two arrays has the same shape or the same type or the same model for now. So we can say, why not? We can answer the SMRQ of the array X is equal to the position of the SMRQ of the array Y. If this array is X, and this is Y. Let's take an example here. For example, the SMRQ on the whole array is at position 2. 0, 0, 1, 2. Same here, the minimum is at position 0 of the whole array at position 2. Here 8, here minus 3. The minimum of this sub-array, because this property must hold of any sub-array. This range, the minimum is at position 4. You see. Or here 0, 1, 2, 4, yes. Position 4. Let's take another example, this one. And this one is at position 2. Position 2. This one is at position 1. Position 1. Etc. As you see, because these two arrays has the same type or the same model, we can answer the SMRQ of one is the SMRQ of the other, the position. So we can pre-process these two arrays like this. We can draw a 2D array of size 1, 2, 3, 4, 5. 1, 2, 3. Okay, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So I can say that the minimum from 0 to 0 at position 0, from 1 to 1, 1, 2, 2, 2, 2, 3, 3, 3, 4, 4, 4. This is 3. Just we can get just the idea. It is better drawn as you see, but just to know the idea. For example, here the minimum from 0 to 1 for both is at position 1. The minimum at position from 0 to 2, 0 to 2, the both is at position 2. From 0 to 3 for both at position 2 also. From 0 to 4 for both at position 2. Here 8, here minus 3. Now the minimum from position 1 to 2. 1 to 2 it has position 2 for both. 1 to 3 at position 2. 1 to 4 at position 2 for both. Etc. You can complete this array from 2 to 3 is at position 2, from 2 to 4 at position 2. From 3 to 4 it's at position 4, from 4 to 4 at position 4. So this preprocessing holds for the both arrays because are the same type or the same model. Okay. So if I have two blocks or many or other many blocks of the same type, we can do the same preprocessing for all. So one time, just one time, they do the preprocessing on that type and save it. One way to normalize is do subtract operations between the element and its successor. If the result is positive, we put 1, otherwise we put 0. For example, here, if I take this array, 5 minus 2 is positive result, so we put 1. 2 minus 3 positive result, we put 1. Minus 3 minus 4 negative result, we put 0. 4 minus 0 positive result, we put 1. So we get a binary string that represents that array. So that array could be represented using this binary string. Okay, but this problem has an issue. Let's see it together. This method for normalization has a problem, has an issue. If I take these two arrays, if I apply this method, get the same binary representation. So we can say that have the same type. Okay, but as you see, it's obvious that these two arrays are not the same type or the same model or the same normalization, because it's obvious here the minimum is here, but for this array the minimum is here. So these two arrays are not the same type. So this method does not is wrong method to normalize the blocks. We have to choose another criteria. We have to pick another criteria. There are many criteria to normalize the arrays. I will choose the isomorphism, or what we call the structurally identical. Structurally identical. Sorry for this guy. Which means we're going to draw some tree. Draw some tree for each block, each array. For this one, for example, we have -1, 1, 1 here, 3, 5. Maybe you're asking how we get this tree. Of course, I will answer this in a moment. We're going to explain this very deeply. How to draw or how to construct this array, this tree. For the array on the left, we have this tree: 0, 30, 20, 64, 80. As you see here, these two trees have the same shape. We can say that these two trees are isomorphic or structurally identical. Okay. If I take these two arrays now, let's draw the same trees using the same technique. We'll see it later. This technique, and this array will be represented by this tree on the right. As you see, these two trees have not the same shape, so they are not isomorphic. So we can say these two arrays has different types, but these two array in the beginning and the first two lines are has the same type. We can represent them as by the same binary string. So what's this tree? This tree is the Cartesian tree. You can see the Wikipedia definition of the Cartesian tree. In computer science, a Cartesian tree is a binary tree derived from a sequence of numbers. The smallest number in the sequence is at the root of the tree. Its left and right subtrees are constructed recursively from the subsequences to the left and the right of this number. When all numbers are distinct, the Cartesian tree is uniquely defined from their properties that its heap ordered and that is symmetric in order traversal of the tree returns the original sequence. So I can resume this. What's a Cartesian tree? A Cartesian tree is a representation of the original array. How it will represent? First, it will respect the heap property. It will maintain the heap property. What's the heap mean? We have two properties for the heaps, min and max. So here, because we are looking for the minimum, we have our Cartesian tree must hold the min heap property, which means if I have a parent, all the nodes of the subtree of that parent must be greater than the parent. Because in our array we can find some identical values, so we can say that all the nodes on the subtree of the parent must be greater or equal than the value in the parent. This is the first property of the Cartesian tree. The second property, so if we do an in-order traversal of the tree, we get the same original sequence of the same array. So we have two properties, min heap properties, as we have seen, and an in-order traversal returns the original array. Okay. Let's see an example very quickly how to see these two properties. If I have this array, its Cartesian tree is like this. Let's see if we have the two properties first. As you see here, 2. All the nodes on the subtree of 2 are greater than 2. And let's take another this one, for example. This is the parent of the subtree. All the nodes here are greater than 5, 7, 8, 8. Same here. Of course, this one, as you see. This is the first property. This is a min heap property. The second property, in-order traversal, will return the same subsequence here, or the same sequence, sorry, the same array. What's the in-order traversal? The in-order traversal, I have a node, let's call it root, or parent, if you want. We have a left child, because we have a binary tree here, and a right child. In order to traversal, we have to first visit the left child, or left subtree, and the root, then the right child of the right subtree. let's try with this tree. We have 2, so we go left because we want the left first. We go left, and we go left. There is no left here, so nothing to display here. So we come back to the root. We have 6. Left, there is no left. We come back to the root, 6, and the right child, which is 9. So this left is done. We go to its root, which is 2. Now we go to the right of that root, of that parent. We have a subtree here. We go to the left. We have a node. We go to the left of that node. There is no left here, so we display 4 because there is no left to display. We display 4, which is the root, the parent of this subtree. Then we come back to the right. To the right there, we go left. We have this node. We go left. There is no left here, so we display 7. We come back to the root, display 7, and go right, display 8. So this is done. So done. Okay. Because this left is done, we can go to its root, which is 5. So we display 5, and go to its right, which is 8. Display 8. Now this is done. Okay. So all this is done now. We come back to its root, which is 3. Then we go to right, display 7. As you see, if I apply an in-order traversal, I get the same original array: 6, 9, 2, 4, 7, 8, 5, 8, 3, 7. Now let's see how to build this Cartesian tree. First, we're going to see the naive approach. The naive approach will allow us to understand the mechanism behind the construction of this Cartesian tree. Keep in mind, guys, that we want the Cartesian tree to normalize the blocks. So we have to normalize the blocks to know that what's the type of that block. So we will use the Cartesian tree to see if the trees have the same shape. If the trees have the same shape, so we can say that these blocks, the 2 blocks or the other blocks, are the same type. So the naive approach, we will do a Linear scan over the array to find the minimum value, then recursively processing the left and the right halves of that array. This is the algorithm. If you don't know, guys, how to build a tree using pointers or just using array, never mind, guys, because later we will see we will not physically build the Cartesian tree. We need only its shape, or its let's call it shadow, if you want, guys. I don't know if the term is exact here. We want its shape to build the binary string of the normalized block. So here, just focus on the mechanism, how to build this Cartesian tree. In the code here, we have this piece of code to compute the minimum. It's I think everybody know this. In the array, to compute the minimum first, I will say that the minimum is at the first position. Here, the function will take as parameters the array A, the start position, from where we will start, and the end position, along the last position to end. The minimum, we just said, I will assume that the minimum is at the first place here, and I will update the minimum if I will run over all the rest of the values. I will update that minimum m if I found it is greater than the current value. Okay. This part in the green part here is if I find the minimum. So from the start position to the position of the minimum -1, I will build the left subtree, and from position of the minimum +1 to the end of the array, I will build the right subtree by calling twice recursively the function bit. Here, of course, if this is the base case, if just we have one element in the array, so create a node and recursively go back, do a backtrack. As we know, the recursive call here, how it works. You will do a backtrack to build the nodes node after node. And if, of course, we have no elements in the array, we have no tree, no subtree. Let's run over this piece of code, the pseudocode, and see how it works. First, of course, if we call this function, we call it by a position 0 to n-1. First call of this function. So we will build a Cartesian tree on the whole array. So we will assume at the beginning that the minimum is 6 at position 0, and we will run over all the rest of the elements to find the minimum. 6 is greater than 9. No. Go to the next. 6 is greater than 2. Yes. So the minimum will be updated to 2 at position 2. 2 is greater than 4. No. 2 is greater than 7. No. The minimum 2 is greater than 8. No. No. For all the rest. So we can say now we exit the for loop, and we will go in. This is our node. So this piece of code will be executed now. We will return that node, but of that node, we have to call the same thing, the same function. But now, in the green part, this is the left subtree of the node 2, and we will construct the right subtree of the node 2, because this is the minimum that we have in the array. So the same thing will be repeated for the first subtree and the left subtree. Let's take the left subtree here. So I will say that the minimum at position is 6 at position 0, and we're going to run over the rest of the element of that part of the left part of the array. 6 is greater than 9. The answer is no. So the minimum here is 6. We reached the end of the array here from 0 to 1. So we're going to return the same code here will be executed. We're going to build the left subtree from 0 to 0 -1 -1. So now when we call this function, we fall here, and there is no subtree for on the left here. So we go to the red call if you want to say here the red function here, and execute it on the element map. Okay, this is the left subtree of 2, and for 9, same here. The minimum is 9 at position 1. We have just one element, so this one will be executed here. So we will return the node at that value. This is the right subtree of 6. Okay. Now we come back to the right subtree of 2. We assume that the minimum is 4 at position 3. And we check if for the rest of the element. 4 is greater than 7, no. Greater than 8, no. Then 5, no. Then 8, no. Then 3, yes. So the minimum will be 3 at position 8 for that part of the tree. 3 is greater than 7, no. So we're going to return that node and build the left subtree in green of that node and the right subtree in red, in color red. Same for the green part. I'm going to assume that the minimum is at 4, the position the minimum is at 3, so 4 greater than 7, no. Greater than 8, no. Greater than 5, no. Greater than 8, no. So the minimum here is 4. So we put 4, and we're going to build the left subtree and the right subtree of 4. Here there is no left subtree of 4 because here we have 2, the root 2. This is done by 2. So for 4 here, there is no left subtree. There is nothing on the left here. Okay. Now we come back to this call, which means the right subtree of 3. We assume the minimum is 7 at position 9. So we have just one node here, so just create it, and this is our right subtree. Now we come back to the part, to the right subtree of 4, this element 4. We assume that the minimum is 7 at position 4. We check for the others. 7 is greater than 8, no. 7 is greater than 5, yes. So 5 will be the minimum at position 6. 5 is greater than 8, no. Reach the end of that sub array. So the minimum is here at 5, and we created the node, and we will construct the left subtree of 5 and the right subtree of 5. The left subtree in green and the right subtree in red. Okay. Same. We come back to the left subtree of 5. We start from 7 at position 4. That's the minimum we will assume, and we check for the others. Just one element here. 8 is 7 greater than 8? No. So we can say that 7 is the minimum and is the left subtree of 5. And we're going to build the left subtree of of 7 here, there's no 7 left subtree because it's done by 4, this node here. So we go to the right subtree of 7. We come back now to the right subtree of 5. We assume that the minimum is at position 8, at position 7. We have just one element here, so created, and that's the right subtree of 5. We come back to the right subtree of 7, which is 8 here, just one element, just created. This is the naive approach to construct a Cartesian tree. The idea is to find the minimum and recursively call the function to construct the left subtree and the right subtree of that minimum. I will let's try by yourself, guys, to construct the Cartesian tree of this array. Just pause the video and try by yourself to understand the mechanism behind building the Cartesian tree. Okay. Of course, we have to find the minimum in the tree, which is 1. So now we're going to build the left subtree and the right subtree of 1. Let's start by the left. On the left subtree, we have 1. We have our minimum. We're going to check to build the left subtree on these 2 elements, and the right subtree is this element. Okay. The minimum is 2 on the left, so same here. And let's make left right to make the things more simple. Well, we will construct the left subtree and the right subtree for each one. I will not follow the mechanism of the recursion. So we have 2. On the right we have only 6. We come back to 2. We check the minimum and the rest of the elements from 1 to 9, which is 3. The first, we have 3 3s as you see here. We pick the first one. That's the minimum. So on the left subtree, we have of the 3, we have from 1 to 5, we have 4. And on the right, we have this first 3. This 3. Okay? And for 4, we have to check or to build the left subtree using the elements from 1 to 2, 9 and 12. We have 9 first, this is the minimum. And on the right, we have 7 and 8. Because we will pick, of course, 7 because it's the minimum. And we go back to the 3 here. This is 3. On the left, we have just one element, which is 8. And on the right, of course, we have just one element, which is this 3. We come back to 9. We build the right subtree because there is no left subtree. Because the 2 is done here. There is no left here, because that is done here. And for 7, we have same. We have on the right, we have 8. Okay. This is done. This is your Cartesian tree for this array. As you see, it maintains the 2 properties of the Cartesian tree, which is a mean heap property. And if we perform an in-order traversal, we will get the same original array. Try it by yourself, guys. You will find the same result. Let's talk about the time complexity of this naive approach. In each problem, we do a linear search to find the minimum. We are okay here because, as you see, every time we call this function recursively, we have to do a linear search to find the minimum. And we have here, we have two recursive calls, this one and this one. Okay. Let's say the size of this first call from S to P minus 1 is equal to K. So we have K elements here. So the size of the other is N minus K, of course. Okay. So we can write the recursion, the recurrence relation of the naive approach, which is T of n, our function Fn or T of n is equal Tk, the first recursive call, plus Tn minus k, the second recursion call, plus the linear search plus n elements here of the linear search. Of course, if I have one element, I have just one operation, so T of 1 is equal to 1. If my array is of size 1, we have just one operation to do. There is no other operations. If you're not familiar with this, guys, don't worry. Just a way to push you to learn about this stuff. You can find many lectures in YouTube, especially of a good lecture of MIT. I will show you later, and you will find the links in the description below of this video that speaks of this many lectures that speak of this stuff. If I have this recurrence relation of my function, naive function, let's check for the upper bound. What's mean in the worst case? In the worst case, what's the time complexity using this recursion function? The upper bound, we have to take k is equal to 1. If k is equal to 1, which means if my minimum is at the first position or the last position. So every time I have to run over all these elements or all these elements. Okay? This is the upper bound. This is the worst case. So we will replace k by 1 here. So T of n is equal T of 1 plus T of n minus 1 plus n. Of this type of the recursion equation, there are many methods to compute to resolve it. There are many ways to resolve it. One way is called substitutions. We will substitute each term T of n or n minus 1 or any other T of n stuff by its value, which means here, for example, T of n minus 1, we will substitute it by T of 1 plus T of n minus 2 plus n minus 1. It's very obvious here. If T of n is T1 plus T n minus 1 plus n, so T of n minus 1 is T of n minus 1 is minus 2 plus n minus 1. Because here, you see, here we have n, here 1 is constant here. This one, we can replace it by this T of 1, this T of 1, and T minus 2, because here we have T n minus 1, so we will subtract 1 from n minus 1, we get n minus 2, and here we have n, so because this is T minus 1, we have must T n minus 1. Okay. If we replace t of n minus 2 by its value, it will be t 1 plus t of n minus 3 plus n minus 2. Okay. If we do a lot of substitutions, we can say that at a next point, we have x times t of 1. Like here, guys, we have t minus 3. We have 3t of 1 plus n, which is the first one, plus n minus 1, the second one, plus I minus 2 of this n minus 3. Because here we look for I minus 2. Okay? If I have x terms here in the function, I can say so. We have x of times the t of 1 plus t of n minus x plus n, I minus 1, I minus 2, I minus 3, I minus until n minus what? N minus x minus 1. Okay? Because here, as you see here, we have n minus 3, we have for the last term here is I minus 2. For I minus 2, the last term we have n minus, we have 1. For n here, we have here 1. So here n minus, we can say 1 minus 0. 1 minus 1, sorry, to get it. Okay? We can write this if in the base case now. What's the base case? The base case, we can, before the base case, we can write this function, use like this, x times t of 1 plus t n minus x, nothing changed, plus how many x, how many n we have here? From here to here, we have, from here to here, we have x minus 1 n. Okay? And plus this n. We get xn. So here, we can say this one, n plus n minus 1 plus n minus 2 plus n, etc. We can get x n. And we have minus 1, minus 2, minus 3, minus 100 until minus x minus 1. We can write it minus 1 plus 2 plus 3 plus until x minus 1. This sum can be computed using the famous formula, this one. So plus xn minus x minus 1 times x over 2, because we know the sum of consecutive integer from 1 to, let's say, x is x times x plus 1 over 2. This is a well-known formula. We don't need to prove it, guys. But we have here x minus 1. So will be here x minus 1 times x minus 1 plus 1 will be x over 2. In the base case, what's the base case here? The base case to get one element, so which means n minus 1 is equal to 1. This is the base case. We have just, we go x, we will go until n minus 1, n minus x will be equal to 1. So we can say that x will be equal to n or n equal to x. So we replace x by n, we get this formula, n plus 1. 1 is Why n? Why just n here? Because n plus n times 1, because here is equal to 1. Minus that formula, we substitute x by n. So we get in the final this function. This is our function here of this recursion equation. So we can say that we will take, we don't need to prove it here, we will take the upper bound directly, which means the asymptotic upper bound of this function. No need to do it every time. So we will get a quadratic with time complexity for the upper bound in the worst case. What's about the lower bound? Which means lower bound if the minimum is always at the middle every time. So we will divide the array by 2. K is equal n over 2. So we substitute k by its value. Our function Tn is equal t of n over 2 plus t of n over 2 plus n. We can write it 2 times t of n over 2 plus n. We substitute t n over 2 again by the value. If Tn is equal to Tn over 2 plus Tn over 2 plus n, so t over n, t of n over 2 is equal of t n over 4 plus t of n over 4 plus n over 2. We can write like this. It's 2 times 2t n over 4 plus n over 2 plus n. We can write like this. It's 4t n over 4 plus 2n. Okay. In general case, we can say after x operations, we can get x times t over n over x over t, x times t of n over t power x plus xn. Okay? Because this one, the first one is 2 power 0, the second one is 2 power 2, this one. If I continue, I will have n over 8, etc., which is 2 power 3, so 0, 1, 2, 3. So we can write like this, this formula. Okay? In the base case, so we will get just one element here, which means n over 2 power x is equal to 1, which means x is log base 2 of n. So we substitute n x by log 2 of n, we get this formula. We can get x log of 2 of n plus n log base 2 of n. To compute the lower bound, we compute the asymptotic lower bound of this function. We get omega n log n. So the naive approach, the best case could be n log n. Okay. How to build efficiently this Cartesian tree now? Before we go to this part, guys, to this section, to this part, you have to understand how to build the Cartesian tree using the naive approach, or build the Cartesian tree in general. We must do this efficient approach, because keep in mind, guys, that we want our preprocessing time complexity in linear time. So the construction of the Cartesian tree must be linear. We will see now an efficient approach of building the Cartesian tree. So we take 6, then We have 6 as the first node. We do nothing here. And we go 9 to 9. We see that 6 is greater than 6 is not greater than 9. Okay, 6 is not greater than 9. So we can say that 9 will be the right subtree of 6. Because there is no left subtree for 6 here. We go to 2. What will happen now? We check. We will construct the left subtree of 2. We check if 9 is greater than 2. The answer is yes. So 9 could be in the left subtree of 2. Could be the parent of the left subtree of 2. We go back to 6 now. We have 6 is greater than 2. So we change this link. 2 will be pointed to 6, which means 6 is the parent of the left subtree of 2 to maintain the mean heap property. All these nodes must be greater of 2. Let me see. Go to 4. Is 2 is greater than 4? No. So 4 will be the right subtree of 2. We go to 7. 4 is greater than 7? No. So 7 will be in the right subtree of 4. Why we don't check 2 here? There is no need to check 2 because we are sure that 4 is greater than 2. And we have found that 7 is greater than 4. There is no need to check 7 and 2. We know that these two nodes are both greater than 2. So both are in the left and the right subtree of 2. We go to 8, same here. 7 is greater than 8. No, so 8 will be in the right subtree of 7. We go to 5. We check, is 8 greater than 5? The answer is yes. So 8 could be the parent of the left subtree of 5. We go back to 7. We don't stop here, guys. Why? Because it could be another node greater than 5 that must be included in the left subtree. So we have to check the elements here. We go to 7. 7 is greater than 5. The answer is yes. So we change the link. 7 is the parent now of the left subtree of 5. We go to 4. Is 4 greater than 5? The answer is no. So we are sure now that these two elements, 7 and 8, are in the left subtree of 5, and 7 is the parent of the left subtree. All of them are greater than 5. Now what will happen? 4 is greater than 5? No. So 5 will be the right subtree of 4. Why this? Because as you see here, we have 8 greater than 7, 7 greater than 5, yes, and 5 greater than 4. It does not make sense to keep this link here because 5 is greater than 4 and 4 is pointed to 7. So there is no need to keep this link here. 4 must be linked to 5 because we want to have all the right subtree here of 4 must be greater than 4. Okay. We go to 8. 8 is greater than 5, so 8 could be the parent of the right subtree of 5. For 3 now. 8 is greater than 3. The answer is yes. So 8 could be the parent of the left subtree of 3. We go to 5. Same for 5. 5 is greater than 3. So 5 will be the parent of the left subtree of 3 for now. Now the question, will we check 8 and 7? The answer is no, because 8 and 7 are checked by 5 before. We have done this for 5. So we have found that 5 is greater than 3. So we are sure that every node below 5 is greater than 3. So there is no need to check 7 and 8. Okay? We go to 4. 4 is greater than 3, yes. So we say that the left subtree of 3 is 4. Start from 4. So we are sure now that all these nodes are greater than 3. And now we check if 2 is greater than 3. The answer is no. What we're going to do now? Of course, this link must be changed. This one does not make sense that what we say that 4 is the parent of the right subtree of 2, because we have found an element lower than 4, which is the 3, and greater than 2 in the same right subtree, in the same right side. So we have to change this link. Okay. We go to 7. 7 here is greater than 3, so we say that 7 is the right subtree of 3. This is the mechanism of this efficient approach to build this Cartesian tree. Of course, we will make more examples and we will see the code and how to execute the code manually. I will give you some second. Pause the video and use the same principle here to build the Cartesian tree of this array. Of course, guys, if the time is not enough for you, you can pause the video and try many times to understand the mechanism of this efficient approach. We start from 2. We have nothing here. We go to 9. 9 is greater than 2. The answer is yes. So we can say that 9 for now is the parent of the right subtree of 2. We go to 12. 12 is greater than 9. So we can say that 12 is the parent of the right subtree of 9. We go to 4. 12 is greater than 4. The answer is yes. So we can say that 12 is the parent for now of the node 4, the left subtree. We check for 9, of course. 9 is greater than 4. The answer is yes. So we change the left subtree. The parent of the left subtree of 4 is at 9. Now, 2 is greater than 4. No. So we have found a node that is lower than 2, greater than 2, sorry, on the right side, on the left subtree. We have found a node greater than 2, which is 4. But and 4 here has as left subtree 9 and 12. So it does not make sense to keep this link from 2 to 9, this one. So we have to change here to this to 4. We say like this, that because 9 is greater than 4 and 4 is greater than 2, then we have to say that the right subtree of 2 is start from the root from the node 4. We go to 7. 7 is greater than 4, the answer is yes. So 7 will be in the right side of 4. 8, same for 8, 7 and 8, right side. For 3 now. 8 is greater than 3. The answer is yes. So we can say that for now 8 is the parent of the left subtree of 3. We check for 7. 7 is greater than 3. We can say no, as you see, 7 will be for now the parent of the left subtree of 3. We check for 4, we come back to 4. Is greater than 3, so we change. This will be the parent of the left subtree of 3. We come back to 2. As I have said in the previous slide, there is no need to check for 12 and 9 because it's done. We are sure that are all of them greater than 4. And 4 is greater than 3, so there is no need to check these two numbers. We come back to 2. 2 is greater than 3? No. So we have found on the right side of 2 a node which is lower than 4, the subtree of 4, and greater than 2. So we will change this link. It's very obvious here. We go to 8. 8 greater than 3, so right side up to 3. 3, for 3 now, 8 is greater than 3. Yes, so 8 will be the left subtree of 3. We go back to 3. 3 is greater than 3? No. So we keep it like this for the left subtree of 3, and we will change it here because we have found a node that is on the right side, this node, that is lower than 3, this subtree, but is not greater than this node. So we have to change this link here, like this. So we say that this node, its subtree is start from here, not here. We go to this 3 now. Same here. The 3 is greater than 3. No, so we can write right side. We go to 1 now. For 1, what will happen for 1? 3 is greater than 1, this 3. We test this 3. The answer is yes, so we can say now, for now, that 3 will be, for the moment, for now, the parent of the left subtree of 1. We go back to this 3. 3 is greater than 1, the answer is yes, so this one will be on the left subtree of 1, the parent. So no need to check for 8. And here we go to this 3 now. Okay. We are here. We go to this 3. Is it greater than 1? The answer is yes. So look here. Because this node is greater than 1, we will say that this node will be the parent of the left subtree because we have found a node that is greater than 1 but we can say that lower or equal to this subtree. So we will change the link here of the left subtree. Same here now for 2. We don't have to check all these nodes because we are sure that all these nodes are greater than 3. This one. 2 is greater than 1. The answer is yes. So the same thing here. We will say that the left subtree of 1 will start from 2, because we are sure we have found a node, which is this node, 2, greater than 1. So all the nodes, we are sure that all the nodes below that 2 is greater than 2. So we will make this link. Okay. For 6 now, 6 is greater than 1. The answer is yes. So we make it as the right subtree of 1. So this is the Cartesian tree of that array. As you see, it's the same one found with the naive approach. Okay. As we see, it maintained the 2 properties of the Cartesian tree, mean heap property, and in order traversal will give me the original array. Let's see the algorithm now. The algorithm of this Cartesian tree, same for the node here. There's no need to understand this, guys, because later, as I have said previously, we don't need to build the Cartesian tree at all. Okay. First, we're going to use a stack to store the nodes, and here for this we're going to run over all the nodes in linear time for loop. For each node, we're going to build or process the left subtree when we found a node in the stack that is greater than the current node. So the left of that current node will be this element in the stack, and you pop it. If the stack is not empty, so the element of the stack, the top element of the stack, will be the right of that element will be the current node. Else, if the stack is empty, so the root will be that current node, and you push every node to the stack. Let's see how run this on this example. First, we start from 6. So my current node is 6 here. We have the stack is empty. There's no node to check. So the current node will be the root will be that current node, and we push 6 to the stack. Okay, we go to 9. 9 is my current node now. We check, is 6 in the top here of the stack, is 6 is greater than the current node 9, and below the scale is here in green, 9. So the answer is no. So we do not enter the while loop here. We skip the while loop. The stack is not empty, so we will say that the element in the stack, the top element of the stack, the top of the stack here, its right will be that current node. Oh yes, of course. The element of the stack, its right will be the current node. So we will say that it's the right element here, the right of the element of the top of the stack will be the current node, or the current node will be on the right subtree of the top of the stack. We push 9 to the stack, we push every element, and we come back to next element. The current node is 2 now. We check, is 9, this 9 and the stack, the top of the stack, is greater than 2, the answer is yes. So that current 2, the left of the 2, will be the top of the stack, which is 9 here. And we pop 9 from the stack. Say we check stack is not empty, check is 6, the top of the stack here. Top of the stack 6. Is it greater than the current node 2? Yes. So the current node, which is 2, its left will be that top of the stack, which is 6. And we pop 6 from the stack. The stack is now empty. So we exit the while loop, and we change the route to the current node because the stack is empty. And we push 2 to the stack. We go to 4. My current node is 4 now. My current node is 4. I will test. If the top of the stack is greater than 4, the current node, the answer is no. So the stack is not empty. I will say that 4 will be in the right subtree of 2. So the current node 4 will be in the right subtree of the top of the stack, which is 2. We push 4 into the stack, and we go to the next element, which is 7. 7. 4, is it greater than 7? The 4, always we check the top of the stack if it is greater than the current node. If yes, we do this stuff, left subtree. If no, and the stack is not empty, we do this stuff to build the right subtree. So 4 is not greater than 7, so we build the right tree, which is 7, the right tree of 4. And we push 7 to the stack. We go to 8, current node is 8. 7, is it greater than 8? No. So we will not build the left tree here. We go to the right subtree of 7. So 7, the right subtree of 7 will be 8, the current node. We push 8 to the stack. We go to 5. The current node is 5 here. Now we test. If 8, the top of the stack here, check the stack. If 8 is greater than 5, the current node, the answer is yes. So I will say that the left tree of the current node will be for now 8, which is the top of the stack. And we pop from the stack. And we check for the other elements now. 7. Is 7 greater than 5? Yes. So the left subtree will be at 7 or 5. And we pop 7 from the stack. We check, is 4 greater than 5? The answer is no. The answer is no, so we exit the while loop. Okay? And we check. Now this stack is not empty. The element on the top, we are sure now that the element on the top is lower than the current node. Okay? Is lower. So, and we, in the for loop, in the while loop, we process the left subtree of 5. So we are sure that all the elements in the left subtree of 5 are greater than 5. And this element on the top of the stack is lower than 5 here. We are sure because we quit here. Okay? We are sure that element is lower. So we can say that now that the element that exists on the top of the stack, its right subtree will be the current node. We make this link. For the left of 4 will be the current node. The right of 4 will be the current node. And we push 5 to the stack. And we go to 8. We go to 8. 8 my current node. I check, is 5 greater than 8? The answer is no. So we will say that 8 will be the right side of the current node. Okay? We push 8 on the stack. We go to 3 now. We check if 8 is greater than 3. The answer is yes. So we will process the left subtree. So we can say now that the left subtree of 3, the current node, will be 8, the top of the stack. Okay? For now. And we pop 8 from the stack. And we check for 5. Is 5 greater than 3? The answer is yes. So we can say that the left subtree of 3 is at 5. And we pop 5 from the stack. Is 4 is greater than 3? The answer is yes. So the left subtree of 3 is at 4. We pop 4 from the stack. Is 2 greater than 3? The answer is no. So we are sure now, if we quit this while loop, we will find that the element of the top is lower or equal to the current element. And in the while loop, we processed the left tree. Okay? And the left element, in the left subtree, is processed by this while loop. So we are sure that all the elements below 4 here are greater or equal to 4. So 2, we are sure that the element on the top here, which is 2, is lower than 3. So we can say that now the right subtree of 2 is that current node. And we push 3 to the stack, and we go to 7. Is 3 greater than 7? The answer is no. So we can say that the right subtree of 3 is 7, and we push 7 to the stack. As you see, we reached the end of the array, but we have elements in the stack. We don't never mind about them, because the job is finished here. We built our Cartesian tree using this efficient approach. Let's see the time analysis of this approach. As you see here, we have a for loop here for each element on the tree. How many times we will push this element and pop it. Each element in the array will be pushed at most n times, where n is the size of the array. We have n times here. And of course, if it will be pushed one time, each element will be at most pushed one time to the array. and of course would be popped one time. So here we have, for all the elements, we have n pushes and n pops. Each element is put into the stack at most once, and when it's created for each element, just one element. And same for the pop operation. Therefore, there are at all we have on pushes and big on pops. So the runtime, we can say it is O of n. Of course, we can prove this using the asymptotic upper bound technique, if you want. We have here the sum from I equal to 0 to n minus 1. How many operation here we have? Let's say we have just here, let's call it, let's see constant time here. One operation for each node. We have one operation, 2, 3, 4, 5, 6. Let's say 6 or k operation. So because we have said that for each element it will be pushed one time, just one time, and popped one time. So for all the elements it will be pushed n times. We can compute this and find that is we can get this algorithm in linear time. Keep in mind, guys, that the Cartesian tree will help us to normalize our blocks. What's the Cartesian tree number? There are at most 2 time bs stack operations during the execution of the algorithm. We have bs pushes and no more than bs pops, where bs is the size of the block. So we can represent the binary string of length 2bs bit like binary string, where 1 means a push and 0 means a pop. And we will fill the end with a 0, pretend we pop everything from the stack. If I come back to the algorithm here, as you see here, we're going to, when we do a pop operation, we put 0 on the binary string, and when we do a push operation, we put 1, and at the end, as we have seen in this presentation, at the end there are some elements, remain in the stack. So we have to pop this element and fill the binary string with 0. So here no need to build the Cartesian tree, because all what we need is the binary presentation. We need only the shape of the binary of the Cartesian tree. So this Cartesian number will help us to normalize our blocks. So we will use the Cartesian tree for normalization. Let's take an example here. As you see here, the algorithm is changed. We use the stack. We have a string called norm here, empty string at the first moment. And when we pop, we put 0 at that string, and we when we push an element to the stack, we add 1, and at the end we pop everything and we add 0 to the binary string. Let's run this example very quickly. We have 6 at the first time, so we push 6 to the stack. So we add 1 to the binary string. 9, 6 is greater than 9, no, so we push 9 and we add 1 to the binary string. We go to 2, 9 is greater than 2, yes, we pop 9 when we add 0. 6 is greater than 2, yes, we pop 6 and we add 0, and we push 2, we add 1. We go to 4. 2 is greater than 4, no, so we push 4 and we add 1 to the binary string. We go to 7. 4 is greater than 7, no, so we push 7 to the stack and we add 1 to the binary string. Same for 8. Push 8 and we add 1 to the binary string. We reach 5. 8 is greater than 5, yes, so we push 8 and we add 0 here. 7 is greater than 5. We pop 7 and we add 0 here. 4 is greater than 5, no, so we push 5 and we add 1. We go to 8. For 8, 5 is greater than 8, no, so we push 8. We add 1 to the binary string. We go to 3. 8 is greater than 3, yes, so we pop 8 from the stack and we add 0 to the binary string. 5 is greater than 3, yes, we pop 5 and we add 0 to the binary string. 4 is greater than 3, yes, we pop 4 from the stack and we add 0 to the binary string. 2 is greater than 3, no, so we push 3 and we add 1. We go to 7. 3 is greater than 7, no, so we push 7 to the stack and we add 1 to the binary string. Then we pop everything from the stack when we reach the end of the array. Pop 7 at 0, pop 3 at 0, pop 2 at 0. This is the binary representation of that array. This is the shape of the Cartesian tree using this algorithm. Okay. How many types we can get here? How many types of normalization we can have in this using this algorithm? As you see here, let's see the size of this binary string: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. 20 is the double of the size of the array. The array is size 10. So, as we have said in the previous slides, we're going for each element we have a pop, a push at most in the worst case. So at the end we have n pushes and n pops. So at the end we have 2 times the original array. The binary string is of length 2 times the size of the original array. So here, if the original array of our blocks are of size bs, we have 2 times bs, the size of the binary string. Okay. Let's count the number of types. If I have, if let's suppose that the block size is equal to 1, so like here, so I can have 2 times 1 bits on the binary string, so which is 4 types of normalized block. We can get 4. We can get 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. If we have 2 bits, we can get a block of type 0, 0, or 0, 1, 1, 0, 1, 1. So at the end, in the worst case, I can have 4 types if I have a blocks of size 1, which means 2 bits. Okay. What if I have a blocks of size 2? I can get 2 times 2, so 4 bits. So I can get 16 types. Size 3. The blocks of size 3, I can get 64 types of normalized blocks. So we have a pattern. BS1, if the block size is equal to 1, we have 4, which is 2 power 2, which is 2 power 2 times 1. For 2, we have a 2 power 2 times 2. For 3, we have 2 power 2 times 3. In general, I can say, if my blocks is of size BS, I can get the number of normalized block, or of number of types, is 2 times 2 times BS. Of course, we have to prove this formula. You prove it using induction, of course. It's very simple to prove it. But I will not bother you with this, guys, for the moment, because it's really easy to do. So the pre-processing time complexity to pre-computing all the answers of all the blocks. In the worst case, it could be big O of 2 times 2BS times BS squared. As we have seen in the first place, I will pre-compute all the answer. In the worst case, sorry, I will compute all the answers here. If I have 2 times BS block, 2 power BS, 2 times 2 power 2 times BS blocks, and the size of the array is log to n times log to n. So at the end, I will have this pre-processing time complexity. So the number of blocks, if block size is log base 2 of n, will be 2 times 2 power 2 times log base 2 of n, which is n squared. And to build it to the array, if each block costs, of course, log base 2 of n by log base 2 of n squared. Okay. So the all-time complexity will be this one. You may be wondering how we can get n squared here. It's very simple. Let's see it together. We have 2 power 2 times log base 2 of n. It could be written like this: 2 log base 2 of n power 2. Okay? Or here, power 2. We know that 2 log base 2 of n is equal to n. So this will be n squared. So the time complexity of the preprocessing, if we keep the block size log base 2 of n, is big O n squared times log 2 square of n. Log base 2 square of n. And we want to get the pre-processing in linear time. This is not linear time, as you see. So we have to choose a block size that allow me to get a linear time pre-processing. We have shown for block size is equal to log base 2n, log base 2 n. The time complexity will be O n squared here. Change this formula. Here base 2n, and here we have n squared. Okay. First, let's show that using this formula, this one, we have to show that if BS increases, This formula increase to this formula 2 power 2 times bs square will increase to will be greater or equal of n at some point. It's very simple to use it. To prove it, let's take this function f of bs is equal to power 2 times bs square. We know that if bs increases to plus infinity, the limit if bs goes to plus infinity of 2 power 2 times bs is plus infinity. It's very obvious. And the limit of bs square of bs goes to plus infinity is plus infinity. So we can say that the limit of f of bs is plus infinity if bs goes plus infinity. So if bs increase, this formula will increase too. Okay, so we can say that if bs go to the plus infinity and this one increase, this one is constant, so all the whole formula will be increased to plus infinity. So we can say that at some point, if we do not choose bs, the right bs, that will the time complexity will be more than n or not linear time. So our goal now is to choose a block size small enough to get to power 2 times bs square less or equal than n. How to do that? First, we have to reduce bs to do arrays for normalization block in ON type, and we have to keep the log n factor here. Why? Because as we have seen in the previous part, to remove the log n factor from the preprocessing of the sparse table, the block size must be log base 2 of n. Okay, so we have to keep that. So the idea now, if bs we have to reduce, which means we have to divide log base 2 of n by some integer, positive integer, natural integer d. We have first, we have here our formula 2 times 2 power 2 times log base 2n over d. This is our bs times bs square. As you see, this is bs square. If we choose d is equal to 2, this d. So to 4, sorry. If we choose d is equal to 4. So we have, the formula will be 2 power 2 times log base 2 of n over 4 times log base 2 of n over 4 squared. We can write this 2 times log base 2 of n over 2, because 2 over 4 is 1 over 2. Log base 2 of n over 4 squared. We can write this formula, this one, using the power properties. We know that if m is power of a times b is equal, m is equal m power a power b. Okay, so we can write this 2 power log base 2 of n all power 1/2 times log of base 2 of n over 2 squared. This is, we can write, this is our n here. So n power 1/2 times log base 2 of n over 4. We can maybe ask how 2 log base 2 of n is equal to n, because if I have this log base 2 of n is equal to x, okay, so we can say that 2 power x is equal to n. This is a property of log base 2, okay. This is the property of log base 2. Yes, this is right. So we can write this 2 log 2 base 2 n. If log 2 base 2 n is equal to s, we change this by x. So 2 power x is equal to n. All this is equal to n, as we have seen here. Okay. And we know that n power 1/2 is the square root of n. The square root of n will be, it's the whole formula now. This one is our formula. Square root of n times log base 2 square of n over 16. Okay. So we can precompute the upper bound using the formula of upper bound asymptotic upper bound. As you see here, we can say that k times, if k is the number of operations, k times square root of n is always less or equal than k times square root of n for all n greater or equal to 0. This graph here. This is very obvious here, very clear here, this one. Now, log base 2 square of n over 16, is it always less or equal of square root of n? As we see in the graph here, the answer is yes. For every n greater or for every n greater or equal of, than 1, we have log base 2 square of n over 16 is less than square root of n, as we see in the graph here. Okay, so we can say, if we multiply this to get our function of n, k times square root of n times log base 2 square of n over 16 is less or equal of this product. This product will give me kn. So I can say that fn is a big O of n. So if we choose our BS okay, what's going on here? If we choose our block size is equal to log base 2 of n over 4, we will get a linear time pre-processing of pre-computing all normalized blocks. So let's wrap up here now. If we choose this block size, log base 2 of n over 4, we can build the sparse table on the linear time complexity, and we can say for now this is linear time space complexity too. Okay, and for the pre-computing all the types using that Cartesian tree, the shape of the Cartesian tree, we can, if we choose this block size, log base 2 of n over 4, we can do it a linear time of a pre-process. Okay, and we can say for now that we have linear time space complexity. We focus now on the time complexity. Okay, as we have proved here, if we have this formula gives me the time complexity in general. We have 2 power 2 times the block size types, and we will compute for each type. We'll compute to the array of size bs. So the precomputing of that matrix is bs square. So the all time complexity is 2 power 2 times bs square. So we have proved that if we choose bs small enough, we can get a number that is lower than n. Okay, then we have proved if we choose a number, if we reduce the block size by 4, we divide it by 4, log base 2n by 4, as we have shown here, we can get this formula. And this formula, we have proved that gives me a linear time pre-process. Okay. So the sparse table, it will build like this. And we know the formula of the sparse table. And we will compute all the 2D arrays of the types of each type. Now, how to query now? To query, let's see first, as I have said in the previous part, in the part 1, if you want to compute the minimum from left to right, okay, we have to divide this into sub ranges. The green one here, this one, the green one from L1 to R1 minus 1, we can use the array of blocks and use the sparse table of that array of blocks to get it in a constant time, the query from L1 to R1 minus 1. Now for L1 minus 1 to R1, this part of blocks, we will use the pre-computed answers here. Okay, but first let's see how to compute this L1 and this R1. L1 is as we have said in the previous part, if L is not the start of this block, so we have to compute the start of the next block, which means the first element that's such that is divisible by the block size. The first integer greater than L divisible by the block size. We can find it very, very easily. If L is equal the block size times the quotient Q, this is the quotient Q plus a rest R. We want the integer or L1 which is greater than L but divisible by the block size. If we make this, okay, what's going on here? Okay, L minus R is equal to block size times the quotient. Okay, but here if I subtract R from L, I will get the start of the current block, which means the first integer lower than L divisible by BS, but I want the first integer greater than L divisible by BS. So I will add BS here, L, to get the same BS on the left, on the right side. L minus the remainder plus the block size on the left side is equal to BS times the Q plus BS2. So we can put this together. BS fact times Q plus 1. We can call this Q prime. So I will have L minus R plus block size is equal to Q prime BS. We have shown that there's plus 0, there's no remainder here. There's no remainder because I have, as we have seen here, we add BS here. So I can say that this expression is divisible by BS. So this is this L1. We can do the same for R1. So if L mod BS, how to know if L is not the start of the current block? I will check if L mod BS is different than 0. If yes, so L1, as we have shown now, L minus L mod BS plus BS. Same for R1. Now I will check if R1 or R, if R is the end of the current block. How to know this? If I had some more another block here. Okay, another block here. This is R. To know if R is the end of the current block, this block, just add 1 here, and if R is here, which means R plus 1 will be at the beginning of the next block. If R is the end of the block, the current block, so R plus 1 is the beginning of the next block, which is not the case here. It's not the case because, as you see, R, this is R plus 1, is not the beginning of the next block. How to know that? Just check if R plus 1 mod BS is different than 0. If it is equal to 0, R is the end of the current block. If is not, otherwise is not. Okay, so in that case, we will do the same for R1. R1, sorry, here, R minus R mod BS to get the start of the current block, which means the first integer lower than R divisible by BS. Okay. How to query now? Of course, as we have said earlier, we will use this array of blocks B to pre-compute all these blocks in constant time using the sparse table of the block B, the array of blocks B. And for this part of this block and this one, we're going to use the pre-computed answers. Using the pre-computed answers, the 2D array of each type. It could be the same type or not, I don't know. So, the minimum, it could be at some point here, for this, for example, and here, for example. So SMRQ of A from left to right is equal SMRQ of A from left to L1 minus 1 and union the SMRQ on the blocks B using the sparse table, as we have said. So it will be how to compute this. How to compute this SMRQ on A from L to L1 minus 1. So I have first to find the position of the minimum in the matrix. So here L mod the block size will give me the row here. I don't know, maybe this. This is L mod BS. L modulo BS. Okay? And L1 minus 1 mod BS will give me the column. Here, this one. Will give me the column. Okay? So I have this position. Now, how to get from this position? I have to recover or to get the position on the origin array. How to do this? From that position, I will multiply the number of block here, L over BS, times BS. Is not the same here. This is gives me a value. This is another value. And we will take an example to understand this, guys. Okay. We can use the sparse table to compute the SMRQ on B, and the same here for the left, for the rightmost block here. We will use the pre-computed matrix here to answer that SMRQ. So all of this, it could be done in constant time. Let's take an example here. For example, if I want to know the SMRQ on the original array from 7 to 22, from 7 to 22, okay? All this range. So 7 is not the start of the actual block on the left. So we have to compute the start of the next block, which is L1. As we have seen, L1 is equal L minus L modulo 5 plus 5. 5 here, we assume that 5 is the side block of the size of the block is BS. Okay, so 7 minus, which is the left boundary, minus 2, which 7 modulo 5 is equal to 2 plus 5 will give me 10. 10, as you see here, at the start of the next block from the left. Same for 22. 22 is not the end of the actual block, so we have to, because the 23 we have to add 1, because 23 mod 2 is different of 0. We have to compute R1, which is the start of the current block, which is R1 is 22 minus 2 is R mod 5 is equal to 20, as you see. So 20 here, as you see, at the start of the current block. Okay. So SMRQ now we can compute easily. We can compute SMRQ on the array of blocks B from 10 over 5, which is the block number 2. This is block number 1, block number 0, block number 1, block number 2, 3, 4, 5. Okay, number of blocks in the array B. So 10 over 5 is equal to 2, and 20 minus 1. But why minus 1 here? Because we want the end of the block number 3 here, not because 4 at the start of block number 20 at the start of the block number 4. So we want the end of the block number 3 from 2 to 3. We will compute on using this Sparse table. Okay? So we can say that SMRQ of A from 7 to 22 is equal SMRQ of A from 7 to 9 union, because 9 we can find 9 using this one. This is the start of the next block. Minus 1 give me the end of the current block on the left side. Union the SMRQ of B from 2 to 3 using the Sparse table. Union the SMRQ from 20 to 22. 20 at the start of the current block on the right side, and 22 is the left of the right boundary. Okay. Now how to compute the left part of the range using, of course, the type. We check the type here of this array, which is this Cartesian tree. The same for the right tree here. It's binary representation. If we draw this, we can find this boundary. This binary representation for both arrays. And because these two arrays have the same type, as you see, because they have the same binary representation, we can pre-compute all the position, all the answers, which means from 0 to 0 is at position 0, as you see here. From 0 to 1 is at position 1, 0 to 1. This is 0, 1, 2, 3, 4. Same here, 0, 1, 2, 3, 4. Okay? 2. So from the 0 to 1, the minimum is at position 1, this one. Same here. From 0 to 2 is at position 1, the minimum for both, because they have the same type. From 0 to 3 at position 1. From 0 to 4 at position 1, as you see. We can follow this, fill this matrix. We can preprocess this in, as we have seen, in linear time. So now how to SMRQ from 7 to 9? First, let's get the position of the minimum in of this array. Okay? Which means M, if my matrix is called M, 7 mod 5, 7 is the left boundary, will give me 1, yes, mod, and the second part here for the matrix, and 9 mod 5. 9 is the end of the first block. 9. We can get it from 10. We calculate L1 from L1. Okay, L1 minus 1. So we have M 2, 4, 10, 7 mod 5, mod here, not divided. Mod 5 will give me 2. And 9 mod 5 give me 4. So M24 is equal to 2, as we see here. So the minimum and from the range 7 to 9 is at position 2, is here. Okay. Now how to get this from the original array, which is 7. Which is position 7 in the original array. 7 belongs to the block, let's call it the left block, LB, will be the floor of 7 over 5. 7 is the left boundary, 5 is the block side. We can get 1. So 7 belongs to the blocks number 1. Okay? So how to get 7 now? RMQ of A from 7 to 9 is equal A of 2 plus 1 times 5. 2 is the position of the matrix, M24. 1 is the number of the block where belong 7, the left boundary, and 5 is the block size. We get A of 7. So same here, as you see, we get A of 7, which is 1. Here the minimum from 7 to 9. We do same for the RMQ on the right side, from 20 to 22. Let's see it. First, we get the position in the matrix. Let's change the color here. It's 20, which is R1 here. Mod 5 will give me 0. So 0. 22, which is the R, which is the right boundary. With mod 5 is giving me 2. This one, as you see. So the position, I can say that the position of the minimum and this block will be at the position 1 here. Now we have to compute the index that correspond to 1 in the original array A, which is how 22 belongs to the blocks RB, right block, which is 22 over 5 is equal to 4, belongs to block number 4, as you see here. And we can compute now the RMQ by, we know the position on the block, on the matrix, from the matrix, which is 1. We know the number of block, that block number 4, so we multiply by 5 to get the distance between this index to the original array. Okay, this is 20 plus 1, which is 21. So 1 correspond, the index 1 is the index 21 in the array A. So which is A1 and 21, which is 1, 2. So we can say now that RMQ A7, 22 is RMQ of A from 7 to 9 union, RMQ on B from 2 to 3 union, RMQ of A 20, 22, which is 1, we compute it by the matrix, sparse table, 1 minus 1, the minimum between 1 and minus 9, sorry, and 1 of the right side, which is minus 9. So the minimum, as you see, from 7 to 22 is minus 9 in this range. How to build the array now? We're going to see quickly how to build the array. For example, if what's going on here, I think, okay, I have a problem with colors here. Okay, let's see it from here. If if I have the size of the array is 31, so we'll compute the block size. The block size is log base 2 of n over 4, the ceiling. We have to use the ceiling here because it could be log 2 of n less than 4, it will be 0, so we have 0 point something else. So we get at least we must have 1 as the block size. So log base 2 of 31 over 2 is equal to the ceiling of the 4, 95, etc. over 4 is equal to 2. So the block size is equal to 2 here. as you see. So the array, the size of the array B will be 16, n over bs, the ceiling 31 over 2, so it will be 16, from 0 to 15. Okay. And now let's see that to build this Sparse table, we're going to use the same formula here. I have computed all this, so which is 16 times 5. 16 is the size of the block of the array B, array of blocks, times the floor of log base 2 of the size of the array of block plus 1, which exceeds the set times 5. It will give me the sparse table of this. Normalization, let's check the normalization here. For the two blocks we have just two elements here. We can use the shape of the Cartesian tree. Would give me 1 0 1 0 for this, and for this one 10 32 1 1 0 1. As you see here, we have only two types here. 1 0 1 0 or 1 1 0 0. So we have to build just two 2D array. For the type 1 1 0 0 will be the minimum from 0 to 0 will be 0. The minimum from 0 to 1 will be 0. And the minimum from 1 to 1 will be at position 1. Let's see it here. For example, this one. Minimum from 0 to 0 is, of course, 0. For the minimum from 0 to 1, this is this index 0, this index 1. Minimum from 0 to 1 is at position 0. And the minimum from 1 to 1 is at position 1. This is for this type. For this type, the minimum from 0 to 0 is at 0. But the minimum from 0 to 1 is at position 1, as you see. Okay. Okay. Now, we have proved that using this technique, we can pre-process in linear time. We can get a single query in casted time. And let's see for now, this our extra space complexity. When we write the code, we will see the exact extra space complexity.